And there's still the physical pointer in here somewhere? Ah, good. Thank you. Okay. Good morning, everyone. So I'm going to tell you about, in keeping with the theme of sort of today's talks at this joint session of the Mathematics of Liquid Crystals, the I&I program, and the ICAM summer school, I'm going to, the joint session about photonics. I'm going to kind of tell you about liquid crystal solids and some very kind of broad different things you can do with light and liquid crystal solids, with the hope that this leads into some more kind of specific things that Mark Warner is going to tell you about after the coffee break. So let me give you the quick background. I know that, and also thanks to the organizers for inviting me to speak at this joint session. It's nice to have a big crowd of many different backgrounds. So let me give you a quick refresher on what pneumatic solids are. So you want to think about elastomers first, think about rubbers. So you have some polymer system, you have some crosslinks in it. You can imagine that, might just come off. You can imagine that the polymer is well modeled by a simple random walk, and so you get these spherical conformations of the polymers on average in the material. And this is sort of a very classic theory of rubbers, right? You can cross-link in, and I'm not a chemist, so I'm not the right person to ask about the details of how this is done, but you can cross-link, you can make the polymers with pneumatic side chains or pneumatic main chains, right? So the polymer itself can be made of pneumatic mesogens, or it can have pneumatic mesogens kind of sticking out. And what that does, from a kind of theoretical point of view in the polymer, is it changes the statistics of the random walk. It gives you a bias in a certain direction that the random walk would like to go, lined up with the pneumatic direction of the polymer. So that's a liquid crystal elastomer. There's another step farther still, which is if you cross-link even more and more and more. So on my little cartoon here, there isn't actually that many spots where I could have put in extra cross-links, but so I just put them all cross-linked. But if you cross-link it a lot, you get a polymer glass. And so the main difference, and also there'll be a slide on this in a second, but the main difference you should think about is that things are more constrained, right? You don't get as much rubber response, and you don't get as much free rotation of the director in a pneumatic glass. So why are these possibly interesting? And again, we've heard about this before, but because it's so important to the effects, I want to give you a quick refresher. Upon change of the pneumatic order parameter, you change the degree to which those polymers are lined up along the pneumatics, and so you change the amount by which the statistics of the random walks are changed, right? You change that bias. And by changing that bias, you change the length scales, right? If you imagine starting in an isotropic state and cooling down and increasing the order parameter, you'll get longer directions along, longer length scales along the direction of the director field, and you'll get some Poisson shrinking in the directions normal to the director field. And so these deformations, these kind of microscopic local deformations, are at the heart of all the sort of deformational things that you can think about doing in these systems. All right, so like I said, this is going to be kind of focused on a survey of different things you can do with light. So why or how does light couple to these things? So there are a few different ways. The sort of classic is the wrong word because it's all still so new, but the first way that people thought to do it was to use azobenzene. So you can have azobenzene as a dopant in the system, or sometimes used as the mesogens, where azobenzene is a molecule that reacts. It absorbs light, and it changes from something that does not at all get in the way of the pneumatic order and is actually pneumatic by itself, to this kind of kinked state that frustrates order, right? So you can shine light in a system and lower the order parameter, right? You can get back to the original state, the ground state of the molecule, just by waiting, just a regular old recovery, or you can stimulate it with the right other wavelength of light, stimulated emission. So this is the primary coupling. There's been, I should point out that there are other kind of better molecules out there floating around. Again, I'm not a chemist, so I don't want to get too much into the details, but recently there's been some very nice work done at Wright-Patterson and Alpha Micron on they're calling phototropic liquid crystals, where you actually, the shining of light, it goes the other way around, right? You have something that originally is not a super great nematic former, and you shine light on it, and then it gets more linear. The excited state is the mesogen. And so that, you can switch the direction of the arrows, and if you imagine kind of some spatial patterning with, azobenzene in one place and the phototropic guys in the other place, you could play around with that. That's something that's, I'm not going to talk any more about, but I want to flag up as something that's possibly interesting. Okay, so this is the comparison slide that I promised. So these are the sort of, checkpoint differences between the nematic elastomers and the nematic classes, and some of these are the same, of course. So they both can be activated in a number of different ways. Optical with photonics is what I'm going to mostly think about here, but some of these effects you can also achieve with temperature or gradients of chemical potential or things like that. In the elastomer case, because it's a much lower density of crosslinks in the material matrix, you can get huge strains, right? Here, so you have almost 400% strain, and that's completely fine, totally reversible. Nothing bad happens. And also, because of that much less dense, the lower density of the crosslinks, the director field is free to kind of tip around, and you get the soft mode, which is a very rich elastic system, but it's not something that I want to talk about today. On the glasses, on the other hand, you get the opposite of those things. You get lower strains. You get here, this early experiment on glasses from the Brewer group was kind of cycling at 2% strain, but you can get up to around 5%. And the benefit, though, is that if you wanted to write in a director pattern, it would stay there. You don't have a soft mode. The matrix constrains the free rotation of the director.
What it means G alone? This is then
Sorry?
the G, what it means the G, the load, the limit of the load.
Oh, that's grams. Yeah. This is it's a weight scale. Sorry. Yeah.
Why you don't put the stress? When you have the strain, you have to put the stress.
No. This is you're cycling the order parameter. So you're looking at how much you give it some given load, right? You give it a set load, a set weight on the thing, and at some temperature, right? It has some certain length extent, and then you change the order parameter by changing the temperature, and the material elongates. If you're cooling in, it pulls it up, right? It contracts the other way. It's not a stress strain curve. The stress strain curve. It's a temperature response. You're flexing the weight with temperature. Okay, so I want to give you a sort of very, very broad survey of different ways you can get deformations with photo-actuation in these systems. And so this is just sort of, these are the bullet points. You can have biglass strips, which are the simplest, and I'll actually come back to them. You can have director variation through the thickness of a sample, and you can have variation in the absorption of the light that gives you a gradient in the deformation response. So this is where we're headed. Okay, so in order to do this, you need to kind of set up a simple bending system that you can turn the crank on the elasticity to get somewhere with. You want to relate the stress and the strain. You can do it. You don't need to do the whole fourth rank business because of the Voigt representation and the symmetries of the compliance tensor. So you can cut things down considerably at the first pass. Even better, as it turns out, you don't need to. So this is the compliance tensor in the Voigt representation for a full uniaxial symmetric solid, right? It's got 5 different possible independent entries. However, that's not necessary. As it turns out, you can model, even though the material is fundamentally anisotropic and along a uniaxial direction, you can model them in isotropic elasticity without really losing any of the understanding of the effects. And so you can pass over to just the purely isotropic compliance tensor. So you have a Young's modulus along the primary stress directions, and you get a Poisson ratio elsewhere. So you can write down what the stress is as a function of the strain, just directly take the inverse of that. And so now you imagine that you have your bender, right? And you want it to be, you're cycling some external thing to change the curvature. and you want it to be in equilibrium, right? You want to shine some light on it and to be kind of steady where it is, change the temperature, be steady at some curvature. And so you can just impose the equilibrium conditions and use these, use the four equilibrium conditions on the force and the direction along the bender, the force and the direction. Let's see, so if this is the bender, right, and up, down is the thickness. Actually, there's chalk. All right, so you have long direction of the bender, thin direction of the bender. So you have, so we're going to call this Z direction, this the Y direction, and this the X direction. Okay, so the forces along the long and medium directions and the torques in the long and medium directions should be 0 if you want it to be in equilibrium. And you can back out from specifying what the strains are, you can then back out the properties of the bender from there. And so I should say, well, so there's, just to point out that some of this stuff, this isn't all just theory, these are out there. So this is from Tim White's group. So this is a photo-activated, let me play it one more time, bender where it's...
Is it real time?
Sorry?
Is it real time?
Yes. That's the trouble with having a slide with builds. Yeah, okay. So this is just a bender that's flipping back and forth, right?
Applied only the temperature change. Yeah.
I think this is photo-activated. It looks like it. The next one definitely is. So here you have a much, much stronger light source, and you get this flapping effect. The flapping is higher order because you're getting occlusion of the light source by the end of the bender. Right? It bends strongly, and it bends so strongly that it blocks the light from the front edge. And then when it blocks the light, it goes into recovery, and then it's open again to be bent. Right? So it does this.
Did you measure the frequency?
I'm sure they did. This is from Tim White's group. They did, yes. I don't know what it is off the top of my head.
270 hertz.
There you go. Thank you, Mark.
Thank you.
Right. So now, so those are both splay bend benders. So I should quickly, I use the chalkboard again one more time. Did I put the chalk down here? So in a traditional bender, I just want to be able to compare something. In a traditional bender, you have compressions along the bottom plane and extensions along the top plane, right? And so because of the Poisson effect, if this is extending in the lateral direction, you get some compression. And if this is compressing in the lateral direction, you get some extension. So in a traditional bender where you just have some strip of rubber and you apply some external torques and you bend it, right, you expect to get some lateral curvature developing, which this is at leading order, which turns out to be energetically bad for reasons I'll talk about in a second. But just at the level of the linear elasticity, before you actually think about energetics, you expect this curvature. And so just keep that in mind when we're looking at all the different possible systems that you can use photo-actuation on. Okay, so we have a bender. We're going to put the splay bend texture in it. So the pneumatic on the bottom face lies in the long direction. So if this is the long direction, the pneumatic's like this. And then by the time it gets to the top face, it's tipped up through pi on 2. All right? And then there's no variation along the Y direction, the medium length. You know that, so this is the spontaneous strain that's applied in the frame of the pneumatic director, right? You get the elongation, the strain parallel to the director is one thing, and the strain perpendicular to the director and the opposite, the normal parts of the principal frame is epsilon perpendicular. So you can write down the total strains, which have contributions from the geometry of the bend, right? So you imagine that you're in some partially bent state, and the spontaneous parts that are just the rotations of this into the body frame. And now you turn the crank on the integral conditions from the previous slide, and you find that the curvatures, so these are the curvatures you get in the bender, and these are just the average strains in the directions. So as far as the geometry goes, you don't really care about these terms, but it's nice to know what they are. But for the bending geometry, you find in the splay bend case, you actually don't get any of that extra, you don't get any of this, right? You don't get any curvature in the normal direction to the bender, right? So there's no higher order worries, which you would have if you had that extra curvature that I'll go into detail in a second, because the next system will have it very strongly. Otherwise, you can calculate exactly what the bending is, and you see that it really does depend in the system on the change in the elongations in one direction versus the other. If you had a system that was responding not uniaxially, it was just expanding or contracting the same both with the director and normal to it, this subtraction would give you 0 and you wouldn't get a bend. So it's crucially about the uniaxial director field. Okay, so you get the bend because you have a gradient in the deformation but through the thickness. So another way, instead of doing this to get that, you could have done this, right? You could have twisted through the thickness, right? So by twisting, you still, if you're heating it, right, you're shrinking along the director here, and now you're extending along the director on the top. So again, this is the geometry. So you start along long direction, you end up normal to the long direction, and you do the exact same thing. Again, so we set up the simple linear elasticity bending equations, and you turn the crank. You get very similar looking strain terms. The spontaneous bits are now the same on both guys because you've averaged over the twisting pneumatic. And you find, as I alluded to a moment ago, that your curvatures that you expect at this sort of linear elasticity are equal and opposite. Okay, so that is bad, right? That can't really happen because of the fact that if you have a curvature in one direction and an opposite curvature in the other direction, that gives you negative, that gives you a saddle shape, right? You're curving down this way and you're curving up normal to that, this, like that. Then it gives you a saddle geometry. And a saddle geometry introduces uniform contractions or elongations that are independent of the bending mode contractions and elongations. And that gives you a direct stress term in the energy, which is much worse than the bend term. It goes like 1 over h instead of 1 over h cubed. And so you get strong energetic suppression of this. One sort of very nice way to see, put this down, the sort of things that are going on, and Mark can correct me if I remember this wrong, but I think it was a beautiful presentation by Lamb in the 20s of what happens with, everybody knows what a tape measure is. So a tape measure has an intrinsic curvature in one of its directions, right? It's got this little, putting the cart ahead of the horse there. It's got a little curvature in the groove. And if you try to bend it, right, if you put a bend in the opposite direction, you would think that you're imposing a bend that would create this sort of shape, right? You have equal and opposite bends. But what happens is that's so strongly suppressed that it snaps through completely, and you get a free mode, right? That's now there's no bending at all along the direction that you previously had the bend, and the amount of bending that you get in the new direction is actually exactly the same as the bending you had in the old direction by the energetics, and it's free, right? So this is the sort of strength of the suppression. It's a very, very strong energetic suppression that occurs. Okay. And pointer. Another thing that happens is that if you tip the direction of the director relative to the main body directions, you can force the principal curvature to be some direction other than along the bender, and you can get these twisted shapes. That's just an aside. It's nice. Okay, so bi-glass strip. So this is sort of the easiest, simplest thing you can do. You can just bond some pneumatic glass with monodomain in one direction to some conventional glass in much the same way of the classic bimetallic strip work by Timoshenko, and again, I think in the 20s. And again, you just turn the crank on the strains and you get curvatures out. Now we're in this sort of intermediate regime. H1 is the height at which the bonding occurs relative to the total thickness of the material. And so here we're in this intermediate regime where you get strong bending one way and you get the Poisson amount of the anticlastic bending the other way. Right? So this now looks exactly like traditional bending, right? Where you have some imposed amount of bending and you get, again, to this first order that's then suppressed, a Poisson-mediated curvature the other way. I should say, I think another nice example that perhaps the ICANT people, but probably everyone will appreciate, is that another example of the strength of that suppression is eating pizza. Is anybody, who here has ever eaten a slice of pizza? Feel free to raise your hands. No one has eaten pizza. That's hard to believe. Okay, thank you. 10% of people have eaten pizza. So when you eat pizza, particularly pizza with a thin crust, right, and a large slice, if you try to eat it, just holding the back end of the crust flat, the front, the tip of the pizza that you're trying to eat just flops down, right? It bends down. But if you crinkle, it's taped down. Well, I don't have any paper. If you crinkle the crust up to give it, lateral curvature, the tip doesn't bend down anymore for exactly the same. Oh, thank you, Mark. Yeah. Right. So this is not. It's not shaped like a pizza wedge, but you get the point. Right. So here's my soggy, floppy piece of pizza that I really want to eat. Of course, if I go a little bit of curvature in one direction here, suddenly the tip end there's no more freedom to bend here because of the strength of the suppression. Right? You can't nucleate, you can't support negative Gaussian curvature. Another way, if you're more from the elastic side of things, another way to think about it is that by doing this, you're moving lateral points very far away from the neutral plane as well as another way of calculating the energy, and that also makes it very, very energetically disfavored because you have much larger distance from the neutral plane. Thank you, Mark.
Sorry, what about the adhesion of the mozzarella?
That would definitely help. Yes, that would definitely help. That's a higher order term. Okay, so another thing you can imagine is if you just had a monotomic down, now there's no spatial variation at all in the material. The material is completely uniform. You can imagine affecting a deformation by having gradients in the activation of the material, right? So you shine light on it, and the light, at the face that you're shining the light on is absorbed, very strongly. There's a high intensity, and then that intensity falls off, by Beer's law, into the sample, and so it's just an exponential, and so you can write down this gradient in the strain, right? So you're getting differences in the length changes because of the fact that deeper into the material, it's seeing less of the light that's activating it. Again, turning the crank. So the sort of style of the bending, in a given state, this is a system that is again the same as the traditional, externally loaded bender. But the thing that's interesting about this system is that the actual amplitude of the bend that you get is not monotonic as a function of the thickness of the material, right? And the way to understand that is that if the material and the function, the thickness of the material relative, of course, to the penetration depth, d. And that's what this H star is. I should have written that down. H star is just H over d. That's the scaled thickness of the material. So if you have a material that is very, very, very thick relative to the penetration depth, what's going to happen, right? You'll get some deformation gradients in kind of a thin little surface layer, but then most of the material is just going to be this monolithic block. So it's just going to sit there, right? There's going to be very, very little bending, right? And that comes out from the form of the equation, right? So in the opposite limit, when the material is very, very thin compared to the penetration depth, then there's no relative gradient, for the material to see, right? All the light just hits everything. And then because it's just a big monolithic block with no spatial variance, again, it'll flex. This time it'll elongate, right? But there won't be any bending. So you get, you get this kind of curious, there's a sweet spot in the thickness relative to the penetration depth. And as in the terms of the rescaled H, that sweet spot happens to be at 1/3, right? If you want maximal bending in this kind of system, then you want the thickness to be 1/3 of the penetration depth. And you just optimize the polynomial part of the equation to get that. Okay, what about strong optical absorption? Right, so this was this weak absorption. So in this, I think this is something that Mark is going to talk about. So if the material absorbs much more strongly, you can photo-bleach it. So the absorbers, the little azobenzene molecules, they can all get used up, right? So at some layer, all of them have now bent, and that area will now no longer absorb any light for any active purpose. And if you do that, you have to modulate the intensity as a function of the depth. In general, this actually turns out to be the Lambert W function, but for the purposes of this, we're just going to use an approximation. Just so you know, the limits of the Lambert W function are exponential on the one end, so it matches with the Beer regime, and then linear at the far end. So using just the approximation that I've written down, you get some formula that depends on, so these are the relative, so now there are two different relative parameters. There's the same relative thickness as before, and now there's a relative intensity, right? So now the intensity as a function of the depth is being scaled by this IC, which is a quantity that's related to the degree of back reaction of the molecules, right? So you have the molecules, some of them are turning, and then there is the relaxation state occurs. So you get a repopulation as a function of some time and intensity, in the steady state. And so IC is telling you about that. And so you get this sort of much more complicated thing, and you can imagine there's more knobs to turn. So that's that. And so the final thing I'm going to say about in this part is you can get synclastic response. So I talk all of this was sort of in the regime where you could imagine getting, up to the suppression effects, imagine getting curvature one way and then orthogonal curvature the other way. If you arrange your piece of material, again, just a monolithic block that's a monodomain, where now the pneumatic director is pointing along the direction of the incident light. And then you put on top of that some sort of thickness gradient. So again, an absorption effect, say. There's no difference between any of the perpendicular directions, right? And so the length changes will not be opposite to one another. They'll be the same as one another. And you'll get a sort of, up to the suppression effects, you'll get the material will have a desire to make a sort of little spherical cap. I'm not actually aware of anyone having seen this in an experiment. It would be nice. If anyone knows of anyone that's seen this in an experiment, you can talk to me afterwards. It would be nice to know. Okay, so far, all I've talked about is getting deformational changes by having gradients of response through the thickness of the material, right? And so those of you that heard me talk on Wednesday know that there's a lot that you can do just by changing the director field spatially, right, on the plane of the sheet. And now this is without any change in the strength of the order parameter, right? This is just purely with the director field. So you can imagine asking the question, well, what if you have some spatial pattern in a thin sheet, and you allow the strength of the order parameter to change as a function of your position on the sheet, right? So you can imagine getting a more complicated effect. And the reason why this is tied into the whole sort of photo-actuation is, of course, a very easy way to get a function, a spatial function of a changing order parameter is to have a light beam shining on a surface that gets darker as you move away from some central point, right? You have some profile of the intensity, some spatial profile of the intensity. Okay, so in order to, I think all of you may have seen these, but in case there are lots of other things going on. So I'm going to quickly review the simplest possible case of having a spatial change in the director field, not changing the order parameter as a function of space. but still getting some material change out. So you want to seed a director field that has disclination defect in it. So these are just two examples. I'm going to concentrate on the azimuthal disclination defect. So along, you look at the integral curve, that lies tangent to the director field. This. So everywhere along this curve, this circle in the +1 disclination field, the material wants to shrink, right? It wants to get shorter because you're heating it and you're destroying the pneumatic order. Everywhere along a radius, the material wants to extend, right? And so, and the other version of the +1, things go oppositely, but we'll ignore that for the moment. And so, and again, I said this before, but this limit tells you, because all that's changing is effectively pi, right? There's nothing to cancel off the r cubed here, and this limit is always to 0. But you know it must be a singular limit because of the Gauss-Bonnet theorem and the integral of the geodesic curvature around here changes, but the topology doesn't, so something must be up with the Gaussian curvature inside. And because that happens no matter where you draw the circle, and because this is a singular limit, whatever is happening with the Gaussian curvature must be at the defect. It must be at the central point. So it's actually easy to figure out what it does. It makes a cone. A cone has the exact same change in the ratio of, or at least you can match the change in the ratio of the circumference to the radius for a circle. And you get a nice simple function of the opening angle of the cone and the imposed strain, well, the deformation. Right. So again, this is not, certainly you could actuate this with light, and you could do any of the things I talked about on Wednesday with light. But the thing that's potentially special is not to come, or not yet, it's in a moment. So you could have cooled it, right, or heated the radial sample and gotten buckling. Again, it's just a reminder. All right. Okay. So let's now imagine that we have one of these. Which way did I say? I think I said this is going to be radial. A radial sample, you'll see in a minute. You have a radial +1 disclination, and let's imagine shining a light beam on it that has some spatial variance. It's circularly symmetric and centered on the defect, but decaying in intensity as it moves away. You can certainly also imagine doing what I'm about to say other ways, but light's probably the easiest. You can imagine having the cross-linking density change, for example. Okay, so if we wanted to mimic some surface of revolution, and it's certainly, this is not a perfect example because there's a hole on the top. If you have a flat sheet, a completely flat sheet, you're not going to open up a hole. So you can imagine, you can link the in-material direction of your surface of revolution and the cylindrical radius at the immaterial direction that you're at as a function of that r to the deformation, right? So this immaterial radius, this immaterial distance from the defect to where you end up must just be the integral over the order parameter change, right? The strength of the cross-linking, just radially, right? Because you want to add up, right, the amount by which the radius changes. You have each little differential radial element. This guy here changes by, lambda r0. This one changes by lambda r1, and that might be different. And so you need to add them all up to get a macroscopic length change. And then there's no need to do an integral here. Through the cylindrical radius, you can just relate the desired circumference of the material, because remember, this is all cylindrically symmetric, the desired circumference of the material there with the actual circumference of the surface, right? You just have to match these. You can do a little bit of algebra and moving things around and get a function for the height of the surface in terms of the imposed strain and the assumption that it's a radial, cylindrically symmetric texture. All right, so a quick example. Let's say you want to make a sphere. And so again, the general cases are difficult to solve what the functional form of lambda as a function of space should be, but in principle it is always solvable. It's not, it's just that you have to, you'll probably have to do some kind of numerical integration or something to solve it. The sphere actually turns out to be nice because you can do it analytically. So your height function is just given by this, right, for a sphere of radius big R. You work in rescaled variables. And you plug things in and you move things around from the square root equation from the last slide. And you get this differential equation. Now I said the sphere is easy. It actually depends on what the Poisson ratio is, whether or not it's easy. If the Poisson ratio is just 1, right? So if you imagine some pneumatic glasses have a Poisson ratio of around 1. If you're in some idealized case in a pure two-dimensional rubber, it would have a 1. But anyway, if it is 1, then this is just, there's nothing to this. You just directly integrate it and move, solve for lambda. And you get this simple form. So if you wanted to have a nice smooth sphere pop out of the plane upon illumination, you would arrange the intensity of your light beam to vary with the rescaled distance in this simple way, and you would shine it on a thin radial texture of pneumatic glass. And it would make this little spherical cap for you. Just to say, if this nu were not 1, if it were something else, you can actually still solve it analytically, but it's sort of a bear and not worth going into. You could get a potentially long polynomial in the trigonometric functions and the hypergeometric function 2, 1. Okay, so I think I've sort of taken you through a lot of different things, different ways that you might use light to actuate a photoglass. And I want to thank, in particular, definitely I want to thank Mark Warner, who was my collaborator and advisor on all this work. And also Kaushik Bhattacharya for some help in the theory, and Dick Brewer and Casper Van Osten for some experimental input on some of the Bender stuff. And thank you for your attention.
Thank you very much. There's time for questions. Yes?
So you talked about the difference between a glass and an elastomer.
Mm-hmm.
I was just wondering where the boundary lies.
That's a very good question. I don't know. I'm not sure that anyone knows. It's, the theory of polymer glasses is difficult. There isn't a full microscopic understanding of the pneumatic glasses in particular. And so I think a firm feel for, is there a transition? What kind of transition is there? Where is it? Is not something that we have right now. It would be nice, but at the moment, I think people just, for the most part, if they want to make a glass, they just cross-link it as much as they possibly can, right? There's no sort of fine-tuning. And I might be wrong. Again, I'm not an experimentalist, and if an experimentalist in the crowd knows of a way to fine-tune that, or knows of people that do fine-tune that more, please let me know or let everyone know. But yeah, that's a good question.
Can I answer this question?
Yes, Dick.
Yes. Let's. Many of the. It's working. Okay. Many of the polymer materials have a rather discrete transition between the glassy state and the rubbery state, the elastomeric state, and that's called the glass transition. Yeah. Only in specific cases this transition widens up, and that might create some difficulties with the definition. But many of the materials have, especially the rubbers, has a very discrete transition. So if you cool down a rubber, it directly goes at a certain temperature, in a rather narrow temperature range, to a glassy state.
Poisson's ratio more than half.
Right.
That's
So, yeah. So in the glasses, it tends to be from a half up to as much as 2, usually, which is so for So the question is about. Usually, you think in rubbers, Poisson's ratio is a half because if it's a half, it's volume conserving. But in a glass, it's just not the case. You get, the extensions actually are stronger in some sense. The Poisson extensions are in some sense stronger. And it's probably, and again, there isn't a complete microscopic theory of what's going on in the nematic glasses. I mean, if I were to speculate, I would say that the much, stronger, much more cross-linked environment, causes things when the material kind of moves around to accommodate the director field. There might be some kind of sort of out-of-the-way, non-affine transformations that cause the lateral dimensions to change more than you'd think. But that's just speculation, and there's no...
Stability, linear elasticity can get into problems.
Yeah.
One should notice that one of these Poisson ratios is an optical Poisson ratio.
Yeah, it's the spontaneous
So
Poisson
when
ratio.
when the length changes in one direction, there's by a factor of lambda, there's a length change by a factor of lambda to the minus nu, where that nu is an optical Poisson ratio, and therefore it's not subject to the stability criteria.
For modeling the biglass strips, what was your basic assumption for modeling the bonding in interface?
So the assumption is that so you don't want any slip, you don't want any tearing at the interface. So you need to assume you have a continuous strain right through the interface.
There is no relative strain there.
No. I mean, you have a strain, you have a gradient in the strain,
Okay,
right? You have a function of the strain through the thickness, but you don't have a mismatch.
but it's not true physically.
Well, for the first order approximation, I mean, yes, you can get delamination. Yes, you can get, actual.
You are going to model it?
Maybe, probably not, and that's a no. Yeah.
Thank you.
Okay, on this note, maybe we break for coffee and thank our moderator.